topic of my talk today is why and how zkSNARK works. So everyone probably heard about zkSNARK so far and many times, but I believe that there is not enough of information for people to really understand how it works. And usually it's very abstract and not very concrete to understand. So first of all, why do we need snarks in first place? For example, you need to prove a statement on private data. Let's say you have a hash of your data in a bank account, and you want to prove that you own, let's say, more than X of money to some organization. Or you want to do anonymous authorization. For example, on website, you can sign into the website without revealing who actually you are to access some content or data. Also, for anonymous payments, you know, Zcash. So it's very valuable application. You can also outsource computation. For example, if you have like light client device, you can outsource the computation to cloud service and get result and be sure that it's computed correctly. So for example, it can be some very complex computation like DNA sequencing or something like this. And also scale in blockchain too, because it allows you to outsource computation of blockchain transactions or blocks or even a number of blocks, and you can have like a single proof about like whole state of the blockchain. So what are the properties of zero-knowledge proofs in first place? It's completeness. So this means that you can the prover. So we always have prover and verifier. So completeness means that if prover's statement is correct, it's true, then the protocol will always accept this statement. Secondly, it's soundness. So this means that if prover is not correct, protocol with very high probability rejects this statement. And zero knowledge. This means that the verifier learns nothing about the data. So for example, with bank account, the verifier learns that you have more than X of money, but he doesn't know any other data like transaction history or even how much you have, and so on and so forth. Okay. So what's the medium of the proof for zkSNARK? So imagine this example when you have like an array of numbers and you wanna verify that all the numbers in this array are equal to 1. Yeah. So how you can proceed with this? So for example, you can let's say I'm the prover and there's somewhere verifier who verifies. So verifier wants to see, okay, so every cell in this array is 1. So for example, I can ask, okay, what is so I cannot, let's say we have 1 million of cells, yeah? I cannot really go and see whole array at once. So I need to go one by one and check. So for example, I ask, okay, what is the value of cell number 2? Okay, it's 1. So, okay, now my confidence about this statement that all the values are 1 is like 10% because I checked 1/10 of the array. Second, so I continue forward and forward. So for example, after 5 tries, I'm sort of 50% confident that the statement is correct. But it's a very linear check. So in order to be, in order to have like 99.9% confidence, I need to check really all the cells in this array. And yeah, I always can sort of miss some. So this is why this kind of verification is not very productive. And let's say, imagine if you have millions and billions of this kind of these cells, it will be a very long operation. So let's have a look at polynomials. So on the left, you can see a polynomial, and to the right, it's a graph showing how it looks. So what's interesting about polynomials is that if you modify just a little bit a polynomial, let's say, in this case, we modified last 2 terms. Let's say instead of 11, we have 10, and instead of 6, we have 5. You can see that it dramatically changes a polynomial. And in fact, there is no 2 different polynomials that share any like chunk of a line. So it's always just a couple points. So to prove this, let's have a look how we find intersection of polynomials. So in order to find intersection, we just need to equate those polynomials. So in this case, it equals to x minus 1 equals 0. So basically, this polynomial, the result of this polynomial is the solutions to it are all the intersection points. So in this case, the point 1, x equals to 1, is the actual solution. So basically, these two polynomials share only one point. So this is fundamental theorem of algebra states that two non-equal polynomials share no more points than their degree. So in this case, degree is 3. So degree of polynomial is just its highest exponent of a term. So for example, for any two polynomials that have degree 3, we cannot have more than 3 shared points. So this means that if we evaluate a polynomial, it's like akin to its identity of a polynomial. So in this case, if we evaluate those two polynomials, we'll have two different numbers. And because of this property that I explained to you, if we choose x from the range from 0 to the almost number of atoms in universe, the probability that you will hit the same number, same evaluation, will be 1 divided by the number of atoms in the universe minus degree of the polynomial. So it's quite low. So that's why the polynomials are at the very core of zkSNARKs. So how can we check the knowledge of the polynomial in this case? So for example, verifier wants to check that prover knows same polynomial that he knows. So what can he do? He can just randomly select x and evaluate locally this polynomial. He can send this x to the prover and ask him to evaluate his polynomial with same x and output the result, and he just checks if it's equal. So it's very high probability that if it's equal, it means that they have both of them have same polynomial. This is a protocol to prove knowledge of the concrete polynomial. So, but what if we want to prove some knowledge of properties of some polynomial? So, because in this case we just share basically that we know this concrete polynomial, so we're revealing all the knowledge about it. So, what we do to prove some properties of it? So, for example, first of all, what it means to know a polynomial. So, any polynomial can be expressed in this form. So we have its degree, which is in this case n, and we have the coefficients for each of the degrees. So basically, if you know a polynomial, because x is a variable, what it means that you know just these coefficients, nothing more. Okay? So this is the knowledge of polynomial. So what can we prove about polynomials? So for example, one can be a property like, okay, this polynomial have solutions x equals 1 and x equals 2. So for example, it can be a statement that I know a degree 3 polynomial with this kind of solutions. And this means basically that if we evaluate this polynomial at this axis, we will have a 0 as a result. So these are solutions, or also called roots of polynomials. So let's have a look at factorization. So fundamental theorem of algebra states that any polynomial can be presented, any valid polynomial that have solutions can be presented in this form. So in this case, basically all the A0, A1, and all the A's are the solutions to this polynomial. Why? Because so if you take A and put it as a value of x, basically it will be 0 in this parenthesis, and this means that whole polynomial will be 0. And these are the only solutions to the polynomial. So as many as those parentheses, so many is solutions of this polynomial. So this means basically that if I am the prover, what I need to prove is that my polynomial have this x minus 1 and x minus 2, those solutions, as cofactors of my polynomial. So in this case, this means we need to prove to the, so what is the proof in this case? We need to prove to the verifier that the cofactor polynomial tx is actually part of my, or cofactor of my polynomial px. Yeah. So to find, so my polynomial px is basically just a product of cofactor polynomial and some other polynomial. And to find that other polynomial, I just divide my polynomial by this cofactor polynomial. So for example, it can be, in this case, I have polynomial px, and it can be factored in the parentheses form. And basically, it's already visible that my polynomial has those solutions. So how do I prove to the verifier that I really have those solutions in my polynomial? So verifier again randomly samples R and also evaluates his cofactor polynomial T locally, and outputs this R to the prover. Prover then calculates this sort of other part of his polynomial H, yeah, and he evaluates his polynomial and also polynomial H, and outputs the result. And verifier basically checks that that the evaluation of prover's polynomial equals to this cofactor polynomial multiplied by the other part. So basically, in this case, we were able to prove that polynomial has certain properties. So what about general purpose zero knowledge computation? So for example, if you have this kind of program that depends on some kind of input, so we have let's say W, and we want to, depending on the value of W, it's either 0 or 1, we want to have different kind of calculation. So how do we translate it into the language of mathematics? So this can be easily translated using satisfiability. So basically, this function represents the same calculation, and if you try to evaluate with same values, you will get same results. So basically, if it's 0, it cancels out the first parenthesis and just gets a plus b, and in other case, it cancels second portion and evaluates first a multiplied by b. But how do we represent this as a polynomial? So we need to have a closer look at what is the operation is, because any computation, any program is just a series of operations. So what is operation? It just like elementary operation have just two operands, yeah, left operand, right operand, and the output, and some operator that operates on operands. So for example, 2 by 3 equals 6, so operands 2 and 3, and the output is 6. And if you have more complex, like a cubed, you can just do it in two operations. Yeah. So and let's have a look at properties of the polynomials. So polynomial, if you take two polynomials like f and g and multiply them, what you'll get is basically at every point the evaluations of those polynomials will be multiplied. So for example, at point 1, the evaluation of f will be multiplied by an evaluation of g. So it will be equal to 6, as you can see. So this is a nice arithmetic property of polynomials. And so this means that we can represent each operation as 3 polynomials. So we can have, for example, if for 3 by 2, left operand can be evaluated to 3, right operand to 2, and the output will be evaluated to 6. So if we multiply those polynomials and subtract the output, basically we'll get that this polynomial should evaluate to 0 at point 1. And what it actually means is that this polynomial should have x minus 1 as a cofactor of that polynomial. Yeah, because this is a solution. and only in this case, if the operation is correct. So for example, if we put, in this case, let's say 7, it will be like minus 1, yeah? So, I mean, it will not match. So this is nice property, and for example, this means that the cofactor polynomial in this case for one operation will be x minus 1, and the result of our the operation on polynomials will be x6, as you can see, px, and it's easy to find this other part of polynomial. So for the proof of operation, what we do, we just, again, verify random samples random R, evaluates locally this cofactor polynomial. He also computes this other portion, and okay, so it's actually not correct, but it also evaluates all these polynomials L, R, and O, and outputs it to the verifier. And verifier then basically checks locally that it's correct. So similarly as previously. So, but what how can we do multiple operations? So similarly, as I said, polynomials multiply similarly at every point. So this means that we can represent multiple operations in just 3. So we can represent like millions of operations in those 3 polynomials. Okay, so you can find more about this in the paper that I'm publishing right now, and if you follow my Twitter, you can see also I'm posting links to the Medium article. So, and evolution of blockchain. So this is an application of this particular use case. So basically, what we had is initially we had the Bitcoin blockchain, which allowed us to do just regular payments. Then came Ethereum that allowed us to do any kind of applications on top of blockchain. After that came Zcash, which allows us to do private payments. And so what's actually next? So it seems natural that next will be anonymous execution of those smart contracts. Yeah. So why do you need this in first place? So for example, you wanna hide your personal activity. So if you shop online, people will be able to see all your transactions on the blockchain. So you want to avoid this. You want to be private in this case. Business application. So any kind of business application in the world, it requires all the data to stay private. Otherwise, just enterprises don't use blockchain because they don't want to share their competitive advantage. Record management, like let's say identity, you don't want people to know that you actually change some, let's say your identity is stored on the blockchain, you don't want people to know that you changed something or someone else. So you want all these operations on your identity to be private because it reveals a lot of information. And zkSNARK is in Ethereum. We have zkSNARK in Ethereum, but it's not really anonymous because the transaction origin itself is actually public, and it's just a pseudonymity. So you can easily connect many transactions into one and link them together and understand, okay, this one is happening from this particular account, and it will be easy. It will be very hard to sort of preserve privacy in this case, even if you use zkSNARK primitives inside of a smart contract. So here is a simple demo. I'm sorry. So here's a simple demo of the work that I did. So basically, let's imagine that we have like a simple smart contract that you want to execute anonymously. So for example, it's a call for bids from a governmental organization, and what you have here is just list of bids. You can submit your bid. So let's say you have some keys that somehow hides your identity, and you reveal in the end stage. You have the bid, and you have, and you also require to provide some value. So you need to pay to submit this bid, and also you can get count of all bits that are available. So here is the modified Ethereum client as a parity that allows you to basically do this. So we have 3 tabs here. First one runs the parity client, middle one runs the prover, and last one is just the client to send transactions. So we first instantiate the call for bits smart contract. So we try to query information in this call for bits, what's happening there. So here we can see there is no bits so far. So next we instantiate a confidential wallet in order to be able to transact anonymously with this contract. So here we instantiate this wallet. And at next point we want to mint. So we don't have any confidential money, let's say. We want to mint this money. So for example, we need 200,000 of gas and 50 to send to the contract for the value. So we can see that the value of our balance of our wallet is what we expected it to be. So now we try to transact with this smart contract. So we send 200,000 gas, we send this value, and we post a bid for 1,000 of some currency. So here on the left, there was a zero knowledge proof generating. And here you can see it generates like TZ signature, which basically adds some piece of information to a transaction that allows it to stay anonymous and also pay for its execution. So here you can see the raw transaction, and now you can see that the number of bits increased. So the transaction is successful. And we also can get information about particular bits. So you can see that this data is appearing. And also we can see transaction information. And also note that there is field from, it's empty. So no information about the sender. And those, okay. So how it works, basically, it's modified. So I had to modify the specification of Ethereum. So in blue, you can see those modifications. How it works, the transactions are unlinkable. So if you send 2 transactions, nobody knows that it actually was you. It has, as I said, zero knowledge signature on the transaction. It adds 450 bytes on top. And unused gas returns to the as a confidential money. Any questions? And thank you.